Hello class, welcome to the Stat 312 Chapter 7 Part 2 video. To begin this video, we're going to talk about the model of simple linear regression. Reading from our slide, every use of probability in data analysis is premised on some model. Recall that in the ANOVA setting, we use the fixed effects model to describe the data. To go from the descriptive statistics of our simple linear regression 1 notes to the inference methods for simple linear regression, we must similarly adopt a probability model. The most common or convenient such model is the normal simple linear regression model. This can be described in several ways. To put it into words, the relationship between x and average y is linear, and for a given xy is normally distributed with a standard deviation sigma. Pictorially, we can see this in the following graph, where we have our x and y axis, and our dotted line is our mu of y given x, which is equal to beta naught plus beta 1x, and each point on the line is normally distributed with a mean of our y and a standard deviation of sigma. In symbols, and the one we'll be most familiar with, we say that y is equal to mu of y given x plus epsilon, where mu of y given x is beta naught plus beta 1x. In this equation, mu of y given x equal to beta naught plus beta 1x, this lets the average of the response y change with the predictor x, and epsilon allows the observed response to deviate from the relationship between x and average y. It is the difference between what is observed and the average response for that x. As in the ANOVA setting, we assume the epsilon are a random sample from a normal distribution with mean 0 and variance sigma squared. The normal simple linear regression model is not really that much different from what we used in our textbook for chapters 4 through 6, except that now the mean response is allowed to change with the value of the predictor variable. When it is a sensible description of a real-world scenario, it supports a variety of useful methods of statistical inference with important real-world applications. So to be more clear, in chapters 4, 5, and 6, we would do hypothesis and confidence intervals for mu, population proportion, and the variance. In simple linear regression, we're still going to do hypothesis test and confidence intervals, but instead we're going to focus on doing confidence intervals and tests for beta 1, our slopes, sigma squared, our population variance, and mu of y given x, which is our linear regression line. So first off, let's talk about our parameters of interest, which in this case is going to be beta naught, beta 1, and sigma squared. So the values beta naught, beta 1, and sigma are parameters, meaning they are characteristics of our simple linear regression model to be estimated with our n data points. For us, beta 1 is the rate of change of average y with respect to x. It is the increase in mean y that accompanies a unit increase in x. This second line is a good way if you're asked to describe our slope or rate of change. This is one of the descriptions you should use. Next, we say that beta naught is the y-intercept of the linear relationship between x and average y, and sigma measures the variability in y for any fixed value of x. As estimates of the model parameters beta naught and beta 1, we'll use the intercept and slope of the least squares line, meaning we'll use beta naught and hat and beta 1 hat that we learned in our previous lecture videos. To estimate sigma, we're going to use the root mean squared error, which is equivalent to the square root of our sum of squares error divided by n minus 2, which if we are going to fully calculate it by hand, that would be equivalent to the square root of the summation of the quantity of y minus mu hat of y given x and quantity squared all over n minus 2. And this is a kind of square root of an average squared vertical distance from our plotted xy points to our least squares line. So let's take a look at a quick example. So applying our jump results from our real estate example, we can see that our estimate of beta naught is going to be 16.0081, and beta 1 will be estimated by beta 1 hat, which is 1.90001, and our estimate for sigma will be the root mean squared error, which we will abbreviate as 3.529324. And a good way to interpret the root mean squared error is to use the following. The interpretation of the last of these is that one's best guess is that the standard deviation of y for any fixed home size is about 3.53 or 3,530. Now, as I said, we are going to be concerning ourselves with confidence intervals and hypothesis tests. So let's start off, since we were just talking about our variability, let's talk about doing a confidence interval for our root mean squared error. So coming from our slides, an advantage of adopting the simple linear regression model is that it supports the making of statistical inferences, and in particular, the making of confidence and prediction limits. It, for example, allows us to quantify how precise, beta naught hat, beta 1 hat, and the root mean squared error are at estimating our interested parameters. Now notice they say limits in this instead of confidence intervals. You'll still hear me use confidence intervals quite a bit, but per your book, they refer to them as confidence limits. So let's begin, as I said, by using our confidence intervals to estimate sigma. And doing so, we are going to have this based on the chi-square distribution with n minus 2 degrees of freedom. And so therefore our interval is going to be a bit unique than what we're used to seeing for confidence intervals. Usually it's our parameter plus or minus our critical value multiplied by our standard error. Now, in this case, it is going to be the root mean squared error, which is our parameter of or our estimate of our parameter, multiplied by the square root of n minus 2, which is our degrees of freedom, divided by the chi-squared of alpha over 2, which is going to be our lower bound, to our parameter estimate multiplied by the square root of n minus 2 over chi-squared of 1 minus alpha over 2 degrees of freedom. Well, not degrees of freedom, but confidence level. Where chi-squared of c is the C column with degrees of freedom n minus 2, row entry of table 8.3. And so basically the critical values in our confidence limit for sigma is not the same because the chi-square distribution is not symmetric. So before, when we were saying we could technically look up both values in, say, the normal distribution, but it was going to be the same number, just positive and negative. That's not the case when we're working with a chi-square distribution, so you actually do have to go find two different critical values, which is the two different chi-squared statistics. So to understand exactly what we're going to do, let us look at an example. So in our real estate example, since we know that n is equal to 10 homes represented in our data set, a 95% confidence interval for sigma would be, well, first off, let's think about what information we need to know. So if we recall from our previous knowledge of our real estate data, we were given previously that our root mean squared error was 3.53, which we saw in one of our previous slides. We were just told that our sample size is 10. And now we're also going to be interested in using the chi-square distribution. So we're going to be interested in chi-squared of alpha over 2 and chi-squared of 1 minus alpha over 2. Now, because we were asked to construct a 95% confidence interval, that means our alpha value is going to be 0.05, and 0.05 over 2 is 0.025, and we're going to want 1 minus that. For our upper bound confidence level. So that would be chi-squared of 0.975. And that's going to be with degrees of freedom n minus 2, or in other words, 10 minus 2, which would equal 8. So plugging in our known values, our lower bound is going to be 3.53 multiplied by the square root of 10 minus 2 over the chi-squared value that we're going to have to get from a table, to 3.53 multiplied by the square root, once again, 10 minus 2. Now, at this point, I'm going to pull up the chi-squared table and see what we've got. Now, you can get this from eCampus, but I have the table handy here. This is the same table you have on eCampus. So we're going to be looking for degrees of freedom of 8. And we are interested when we have alpha over 2, which is 0.025. So that should be 17.535. And we also want our chi-squared value at 0.975. And so that would be at 2.180. Okay, so going back to our slides, this was 17.535, and over on our upper bound, it was 2.180. We could go ahead, put this into our calculators, and we would have a confidence limit of 2.38 to 6.76. So in order to appropriately state our conclusion, we would say that one's best guess at the standard deviation of price for a fixed home size is 3.53. But to be 95% sure or 95% confident, one must hedge that estimate down to 2.38 and up to 6.76. So now that we've considered the confidence limit for standard deviation, we should also consider the confidence limit for slope. And this is going to seem a lot closer to what we've done previously, where we'll have a formula of beta 1 hat plus or minus t alpha over 2 multiplied by the standard error of beta 1 hat. Now notice this is going to follow a t distribution, so t alpha over 2 is going to follow the critical value with a degrees of freedom equal to n minus 2. And our standard error of beta 1 hat is going to be equivalent to the square root of our mean squared error all over the square root of SSXX. And we can say that the denominator of the standard error of beta 1 hat increases as the x values in the data set become more spread out. That is, the precision with which one knows the slope of the relationship between mean y and x increases with the variability in the x's. Now, if we're looking at our analyze fit model report, we are very fortunate because we can actually get this information directly from JMP. Under the parameter estimates, we can be given directly the beta 1 hat, the standard error, and if we select the option, we can be given our confidence limit. But as always, we can do this by hand, which we'll do so now. So we are asked to make a 95% confidence limit for the increase in average price that accompanies a unit increase in size. So we know that we have the formula of beta 1 hat plus or minus T alpha over 2 multiplied by the standard error of beta 1 hat. So we know that beta 1 hat, the estimate, is going to be, oops, sorry about that. So plugging in 1.90 plus or minus our critical value, which we'll need to look up, plus or multiplied by the standard error, which from the previous slide we know is 0.2486. All right, looking up our critical value, we want alpha over 2. We were given a 95% confidence interval, so that's 0.05 over 2, so that's going to be 0.025, and we have degrees of freedom equal to 8. So pulling up our t-table, 0.025 and degrees of freedom of 8 will give us a critical value of 2.3060. Plugging into our calculators, we would get 1.90 plus or minus 0.573, which would give us a confidence limit of 1.327 to 2.473. So to state that formally, we can say that we are 95% confident that the true slope, or beta 1, is between 1.327 and 2.473 for 100 or for 1,000 per 100 feet squared. Now at this time, this seems like a good time to do the same as we did in the previous two slides, only for our small fake data set. So I'm going to take a second. I'm going to cut this slide in half. Now, a lot of the numbers I'm going to pull for this are either going to come from slide 90 or slide 97. That's where we did our calculations for the small fake data set. So to start off, let's do our confidence limit for standard deviation. Our small fake data set had a sample size of 5, and in order to calculate the root mean squared error, which we know is equivalent to the square root of SSE over n minus 2, we calculated our sum of squares error to be 1.6. Again, we know our sample size is 5, so this will be 1.6 divided by 3, and then we need to take the square root of all of that. So that is going to be equivalent to 0.7303. And this is information that we got from slide 97. So if we recall, our formula is the square root of MSE multiplied by the square root of n minus 2 over chi squared of alpha over 2 to the square root of our mean squared error multiplied by the square root of n minus 2 over the chi squared of 1 minus alpha over 2. So if we plug into our formula, this would be 0.7303 multiplied by the square root of 3 over a chi-squared value we're going to need to look up. On our upper bound, we're going to rewrite the same thing. And we now at this point need to look up our correct values. So for chi-squared of alpha over 2, again, 95% confidence level. So this would be chi-squared of 0.025 on the lower bound, and for our upper bound, it would be, once again, chi-squared of 0.975. The difference is that our degrees of freedom is going to be 3, as opposed to when we last used our chi-square table. So taking a quick look, again, degrees of freedom 3. So we are looking at chi-squared values of 9.38 and 0.216. So plugging in, we will have a confidence limit of 0.414 to 2.722. And now we can do the exact same thing using our formulas for our slope. Our formula in this case was beta 1 hat plus or minus t alpha over 2 multiplied by the square root of MSE over SSXX. So from slide 90, we know that beta 1 hat is negative 1.2. Our t-table, that is t alpha over 2 with degrees of freedom 3. And so that's going to give us a critical value of 3.1824. Above, we got the square root of MSE to be 0.7303. We know our small fake data set, our SSXX is 10, so we'll need to take the square root of that. And again, that comes from slide 90. Now we can plug into our calculators. We'll get a lower limit of negative 1.93 to an upper limit of negative 0.47. And so there we go. It's really pretty easy, and at this point, kind of old hat for us, given the number of confidence intervals and confidence limits we've calculated previously. Now, in the next step up, I want to talk about calculating the confidence limits for mu of y given x. This is going to be a little bit different, just in the sense that our formula is a little bit harder to use, but it's still, in my opinion, really not that bad. So coming from the slide, the simple linear regression model also supports the making of confidence limits for the average y at a given x star, meaning mu of y given x equals beta naught plus beta 1 x star, where our x star is going to be some provided value. So for example, this could be the mean price for homes of size 11. And so our formula is going to be mu hat of y given x plus or minus t alpha over 2 multiplied by the standard error of mu hat of y given x. Now our t alpha over 2 is going to be the same critical from slide 113, so meaning we have degrees of freedom equal to n minus 2. We know mu hat of y given x is going to be beta naught hat plus beta 1 hat multiplied by x star. And again, x star does have to be given to us. that specific value. Now, the part that's kind of a little more complicated for this is the calculating of our standard error of mu hat of y given x. And this is equivalent to the root mean squared error, all multiplied by the square root of 1 over n plus the quantity of x star minus the sample mean and quantity squared, all over our SSXX. And so some of this requires a bit more calculation than what we've had to do previously. Now, if we're interested in calculating a prediction limit for a y new value at a given x star, that formula would be mu hat of y given x plus or minus t alpha over 2 multiplied by the standard error of our predicted value. The standard error of prediction is similar to the standard error of our mu hat of y given x. It is equivalent to the square root of MSE multiplied by the square root, and here's the difference, of 1 plus 1 over n plus the quantity of x star minus our sample mean and quantity squared over SSXX, which we can actually simplify to be the square root of the quantity MSE plus the standard error of mu hat of y given x squared. So if we are interested in doing an example at this point, we can use our real estate example, and of course we'll do a follow-up one with our small fake data set, but in the real estate example, we consider home sizes of size 2,000 feet, meaning that this is going to be x equal to 20, and we'd like to make a 95% confidence interval for the mean price of homes, and therefore afterwards we'll calculate a 95% prediction interval for the selling price of an additional home of this size. So first off, we need to get our predicted selling price of our home size. Using our formula, we have mu hat of y given x is equal to beta naught hat plus beta 1 hat times our x star. From slide 89, we know that our formula would be 16.008 plus 1.9001, and our x star is going to be 20. So this will give us a predicted selling price of 54.010. So just to write that out, to make sure there's no confusions, for a house of size 2,000 feet squared, the predicted selling price is $54,010, which obviously, remember, this data comes from, I believe, 1986. This would definitely not be the case today. And so now that we've gone ahead and do that, we can now calculate our confidence limit. Using our provided formula, we know that we have 10 homes. Our sample mean is 18.8 and our SSXX is 201.6. And so now we can go ahead and calculate our confidence limit. So this would be 54.01 plus or minus our T alpha over 2, which would be 2.306, our standard error that we've been using, 3.53, multiplied by the square root of 1. Our sample size is 10, so 1 over 10, plus our x star is 20. Our sample mean is 18.8 and quantity squared, and our SSXX is 201.6. So it is a lot of pieces to put together. Now at this point we can simplify. So we would have 54.01 plus or minus 2.306 multiplied by 1.155. So this would give us a confidence limit of 51.35 to 56.67, or just to make it clear, we are saying that the mean selling price of a home that is 2,000 square feet is from 51,350 to 56,670. So now using this exact same information that we've already learned, we can calculate our prediction interval. Before we do that, I just wanted to show when I simplified, I did like write this number out. And remember, the reason I did that is because this is the standard error of mu hat of y given x. And we can use that in our formula when we calculate the prediction limit. So, little trick of the trade. So now we can go ahead and plug in for our prediction interval. Remember, the formula is mu hat of y given x plus or minus t alpha over 2 multiplied by the standard error of prediction. We know that our mu hat of y given x is 54.01 plus or minus, it's going to be the same, t alpha over 2, so that's 2.306 multiplied by the square root of our MSE. So we calculated the square root of our MSE, so this is actually going to be 3.53 squared plus our 1.155. Simplifying, this will become 54.01 plus or minus 8.56. So this will give us a prediction limit of 45.45 to the upper bound of 62.57. So we're saying that the prediction limit for an additional selling price for a home of 2,000 square feet would be from 45,450 to 62,570. And as you'll see in the JUMP video, we can do all of this in JUMP. We can use our JUMP fit y by x report to even visually show what a 95% confidence limit and prediction limit would look like. And using our save column options, we can get our confidence limit and prediction limit exactly. One thing to note in JUMP, for prediction limits, they write it as individual price or individual response. They use the word individual instead of prediction is what I'm trying to get at. Couple little notes here on slide 123. So first note, either by looking at the formulas of the standard error of mu hat of y given x and the standard error of our prediction or the plots above, notice that the confidence interval for mu of y given x and the prediction intervals for y nu are narrowest at the center of our x data set. And this is going to be where our x star, a value of interest, is equivalent to our sample mean. And this is going to make sense for us because we know most about the houses and their selling price that are closest to our mean. And that's generally true of most things, that our mean is the center of our data, so therefore it's the section that we know the most about. And we can also note that if we set our x star equal to 0, which would in this case be a house of size 0 in our confidence limits for mu of y given x, one could make a confidence limit for beta naught. But in practice, this is typically only done when x star equals 0 is inside the range of x values in a simple linear regression set. Why? Well, because we always need to be wary of extrapolation. So yes, we can calculate it, but it is not a great idea. And then sometimes it doesn't even make any logical sense to do so. So as I have promised, we are going to use our small fake data set to calculate our confidence limit and prediction limit with 95% confidence. So for us, if we recall for our confidence interval, our formula is mu hat of y given x plus or minus t alpha over 2 multiplied by the square root of MSE multiplied by the square root of 1 over n plus the quantity of x star minus our sample mean and quantity squared all over SSXX. So using the information from slide 90, we know that mu hat of y given x is equal to 2 minus 1.2x. Remember, our sample size was 5. And for our critical value, that is going to be alpha over 2. So that's going to be 0.025. And we still have degrees of freedom equal to 3. So this is going to still give us a critical value of 3.1824, which we calculated earlier in this video. So at this point, we can now pretty much plug and chug. And we are asked to have our x star equal to 1. So this is going to be 2 minus 1.2 multiplied by 1 plus or minus 3.1824. Our square root of MSE is 0.7303, which we calculated on slide 116. Multiplied by the square root of 1 over 5 plus the quantity of 1 minus 0. Again, that's from slide 90. This is going to be squared. And our SSXX was 10. And again, that's something we came from slide 90. Simplifying, this is going to be 0.8 plus or minus 3.1824. Multiplied by 0.7303 multiplied by 0.547723, which will give us a bound of negative 0.473 to 2.073, which is not too bad. Now, for a second, and I apologize for the pause, I was debating whether I should go ahead and calculate the whole, or rather give you the whole standard error, and that we can use it in our prediction interval formula like I did previously, but I decided let's just go ahead and do it the long way just for thoroughness. And I'm going to change colors here. Hopefully that'll visually might make it a little bit easier. So for our prediction interval, our formula is mu hat of y given x plus or minus t alpha over 2 multiplied by the square root of MSE multiplied by the square root of 1 plus 1 over n plus the quantity of x star minus our sample mean and quantity squared over SSXX. So we don't actually need any new information to calculate the prediction interval. So this is going to be 0.8 plus or minus 3.1824 multiplied by 0.7303 multiplied by the square root of 1 plus 1 over 5 plus the quantity of 1 minus 0 squared over 10, which will give us a prediction limit that goes from negative 1.850 to 3.450. And overall, like I said, I don't feel like these are really that bad to calculate. Long, but I don't feel like they're too hard. Now to wrap up this video, as I said, we are going to focus on confidence intervals and hypothesis tests. Well, we've done the confidence intervals and prediction intervals, but we haven't looked at hypothesis test. And for this video, there's really only one hypothesis test of interest, and that is t-test. So for the normal simple linear regression model, we support the hypothesis testing where our null hypothesis is beta 1 equal to some number, which is generally equal to 0 as usual. It will follow the t-distribution with degrees of freedom equal to n minus 2. And so generally our t-test is beta 1 hat minus some number, and usually 0, over the standard error of beta 1 hat. If we desire, although it is not usual, sometimes we will test our mu of y given x, where the null hypothesis is mu of y given x equal to some number, and our test statistic is t equal to mu hat of y given x minus the value divided by the standard error of mu hat of y given x. Once again, this will follow the t distribution with degrees of freedom equal to n minus 2. But we really are mostly focused on the t-test for beta 1. Why? Because that test can help determine whether or not our predictor is significant or important. Is it useful in predicting our response? So from our slide 126, of the possibilities, the test of the null hypothesis of beta 1 equal to 0 is very common. Notice that in our simple linear regression model, mu of y given x equal to beta naught plus beta 1 x. If we have beta 1 equal to 0, then mu of y given x will be equal to beta naught, meaning that the mean response doesn't change with x. So people usually interpret a test of the null hypothesis of beta 1 equal to 0 in the simple linear regression model as a way of investigating whether x has an influence or effect on y. So formally, what I was saying before is when we are doing a test of beta 1, we are testing to see if our predictor is useful. So if we use our real estate example, one might ask whether there is statistically significant evidence that the mean price changes with home size. So in terms of that test, with the null hypothesis of beta 1 equals 0, then t equal to beta 1 hat over the standard error of beta 1 hat would be equivalent to 1.9001 over 0.2486. We can get this directly from the JMP report or from any of our previous slides, which would be equal to 7.64. We can get all of this directly from slide 128. And then we could compare it to a t-distribution with degrees of freedom n minus 2. We could also do a p-value method if we are interested. In the JMP output, it is going to give you a p-value of less than 0.001, which is tiny. So therefore, we do have enough data to say that the average price does indeed change with home size. So if large p-value means that our predictor is not significant and it's not useful in predicting our response. Small p-value means we have a pretty good predictor. And once again, we can get all of this from JUMP if we have the data. If we are interested in doing it for our small fake data set, using information on our previous slides with the null hypothesis of beta 1 equal to 0 versus the null hypothesis of beta 1 not equal to 0, our t-test statistic would be beta 1 hat over our standard error of beta 1 hat, which would be equivalent to beta 1 hat over the square root of MSE over the square root of SSXX. This is equivalent to negative 1.2, which is our beta 1 hat. Square root of MSE we calculated in this video, which is 0.7303, divided by the square root of 10. That came from slide 90. And this is going to equal negative 5.20. Still using those same rules we always have, we can say that we will reject our null hypothesis. This is a two-sided test. So this is going to be the absolute value of t is greater than t alpha over 2. Our t alpha over 2, we've been using it for many slides now, is going to be 3.1824. So we can see the absolute value of negative 5.20 compared to 3.1824 is clearly greater. So therefore, we can reject the null hypothesis, which means that there is sufficient evidence to infer the mean y changes with our predictor x. Now, in our small fake data set, we don't have any context to add in, but normally we would state this with context. So for our real estate example, when we rejected the null hypothesis, we would say there is sufficient evidence to infer the selling price, the average selling price of a home changes with size. Okay, so that brings us to the end of Simple Linear Regression 2 notes. If you have any questions, please let me know. Have a good night.